Yeah, so thank you very much. So now we move to the somehow scientific part. And it's my turn to introduce Patrik Johansson. So I'm especially grateful for him because he has to rush to the airport just after his talk, but he agreed still to stay and give this presentation. You may know him because he's part of our scientific advisory board. So a few data. So he's a chemist by training, but he was for quite a few years a professor at the applied physics department at the Chalmers University of Technology in Gothenburg in Sweden. His background is spectroscopy and modeling applied to energy materials, in particular battery electrolytes. And he's been also quite active in science managing. He's been co-director of AlixStor, director of the Graphene flagship. And then recently he moved to Uppsala University, also in Sweden, to take over the Battery 2030 Plus, which is the most relevant European initiative at the fundamental science in the field of batteries. So without further delay, Patrik, so grateful to have you here, and the floor is yours. Thank you very much.
Yes. So thank you, Rosa, for inviting me, having me here, and thank you, David, for the scientific advisory board days that we had, and thank you, Javier, for letting me and others very much use this gem, this crystal that is perfected now. And that is really an honor to have that. And Rosa, now you stole a little bit of my introduction, but I was going to say that usually I stand up here and I talk with Ramon yesterday. I talk quite a lot of scientific politics with Brussels and so on in the role of director of Battery 2030 Plus, which is coming into an end actually. So in the future, you will see something called BatBridge, which will be the new European large-scale initiative of batteries. So that is something to learn. It has just started and it will be up and running after the summer. But I'm super happy to also be able to not talk scientific policy, but actually to talk science. And that is something I really want to do. But first, yes, Rosa is laughing because, So one thing for me is that I mean, I don't have 40 years of interaction with ICMAB, but I think approximately 15, 16 years. And some of it comes from the AlixStor network, where I met Rosa for the first time. I think we were in a taxi somewhere in Slovenia, in 200 kilometers per hour, we were both very nervous. And from that meeting, we actually have this beautiful picture where everyone is flooded with rain. And in the morning after, at 4:30 a.m., we took a bus with all our clothes still wet and stuff like that. But I was dry because I'm the photographer of this photo. But also on a more scientific note, this is also something that allowed me to start many of my activities in the next generation batteries was together with Rosa and other people from ICMAB. NIADS was the first big sodium-ion battery project. And today, some of you know, sodium-ion battery is not a next-generation battery technology anymore. It's a technology that is here and present, and it's a complementary to the lithium-ion battery that you have everywhere, and you will see much more of it coming. CARBAT, EIC Pathfinder project on calcium batteries, and calcium batteries is something that Alexander and I still are working together with, and some people here we have Cobra running, and it is truly a next generation battery technology. We are happy if we can get the battery to cycle for 5 charges, which of course you will not be happy with in any application, but that's where we are. But we are exploring things. So to put the battery R&D in context, there are certain things that happens right now. You are all aware about personal electronics, you're aware of electric cars, etc. But the thing is that the electrification comes to everything right now. So it comes to the large energy storages. I mean, of course, we know that's what we heard yesterday also, energy system. We need large-scale energy storage for long-term, medium-term storage, but also ferries or something very, esoteric like some modern plane. But there are things happening here in the practical scale with respect to this that are in some way problematic for people doing battery R&D. Because you see, there is this, let's see now if this works. Yeah. So there is a big high demand, and you can see whatever curves, they're looking like this, all of them. And then you look at the battery prices, and that's like, so everyone is happy, right? Because there is a huge demand and battery prices are falling. What does that mean for battery R&D for us researchers? It means that anything that you do has to be extremely sustainable, because you have to be able to live up to this, that it should be possible to produce quite a lot of batteries, right? And it's not enough, because you also, every solution you do has to compete with these falling prices. That means that every solution you do also has to be very price competitive. And of course, you can say, yeah, we're doing, you know, basic research, etc. Yeah, but this is the end point anyway. I mean, you know better than many of us that we are doing materials research, but we are bringing it to a technology somewhere. So this is actually quite pressing for us. What we're trying. But just putting that into context. So then I was thinking just to bring a little bit on the buzz, what is happening in the world of batteries. I would say that if one looks at what is talked about a lot, it's people talking solid-state batteries. So the big question is, when will these solid-state batteries based on solid-state electrolytes, when will they really materialize? You will see that there are some examples, and people say, yeah, next year. It's always next year. Or it may be a little bit later. So the question is now, are people going rather to semi-solid electrolytes? And then you say semi-solid is not something that exists, because either you're solid or liquid. Semi-solid is when you mix a solid electrolyte with a small amount of liquid, or you do something that is a little bit softer, etc. I think we might be there. Something else, we're bringing on quite a lot of the digital twins and high throughput screening. Quite a lot of AI is coming into the battery world and electrolytes development. And then electrolytes design. That is something that is a buzzword in the world that I live in and the world that we live in. Everyone is talking electrolyte design. And this is something that has happened. So I take you back to the big conference, IMLB, the really big battery conference. I was in Edinburgh. And a typical battery conference at that time was 5 days. And you had approximately half a day of electrolytes, and very much about that was interfaces. So no one was talking electrolytes, but today it's quite a shift. And that is also where ICMAB are very strong, on the battery scale. It is really on electrolytes. And there was also a discontinuity, I would say, between battery people and electrolytes people, because they were not really the same. But what was there for the electrolytes people, that there was a lot of materials characterization. And that you can see then brings ICMAB now as a major player on the stage, that you can do a lot of materials characterization, you can bring it into an application. Yesterday I visited Alba, where you have all these operando tools, and you do operando here as well. This is actually what is happening a lot. So then, remember then, materials are not really batteries, but they're extremely important. I tend to quote something from the DARPA in the 1960s. They had this credo saying that technology is always limited by the materials available. And I think that's so very true. We need to advance the materials to get some technology through. Yeah, so, and this is my sort of world where I go with my research. I play around with lots of different electrolyte concepts. They might be polymers, they might be salt melts, it might be liquids in solvents, etc. And basically they boil down to two different regimes. One is that you have very salt-rich systems, or you have very solvent-rich systems. So if you're a biologist, you would say that, oh yeah, it's like 0.05 molar of salt, something like that. We talk 1 molar is conventional, and then you can go up to 5, 6 molar salt-rich systems. And then another note is that some battery technologies are very limited in the type of electrolyte you can use. But some battery technologies, they can use all of this. They can use all of these different types of electrolytes. It means that the palette that you're using now is quite broad, and you have to focus somewhere to do something. So some target is really to make this kind of semi-solid or solvent-free electrolytes, because this is really what you want to do with solid-state electrolytes. You want to have them solvent-free, because then you don't have leakage, you don't have the fire risk, you have a lot of advantage. You might also have a different conduction mechanism for the ions, and that is really where we're going. And there are some historical things that happen. You had solid polymer electrolytes and composite polymer electrolytes where you mix nanoparticles into a polymer matrix. You don't have solvent there. This is advances by Michel Amand and Bruno Scorsati, and this is actually commercialized in France by Blue Solutions. High temperature operating batteries, high temperature now is 80 degrees or something like that. Ionic liquid electrolytes, something that is very much happening. You don't have organic solvent, but you have ionic, and that is something that Solvionic in Toulouse in France is working a lot with, and also in Japan it's been locked. I will though, however, this one is tricky. I will spend some time with molten salt electrolytes and highly concentrated electrolytes. Concept where you either have no solvent at all, you're making your eutectic mixture, or you have a very limited amount of solvent. So we're trying to get to the solvent-free or free solvent-free. What does free solvent-free mean? It means that all your solvent that you have is interacting with an ion, so that it's not really representative of a solvent as a solvent. Solvent in solvent doesn't really exist, so it's solvent interacting with ions. So how do we understand this? Well, just highly concentrated electrolytes. Taking a traditional, conventional lithium-ion battery electrolyte, you have quite well-defined solvation shells. You have basically cations being dissolved in a solvent, and you can study it by any method, and you will see that it's very nicely organized signatures. Whatever you do, you have quite a little of cation and anion interactions. And this, of course, tells a lot about the performance that you get out in a battery eventually. But if you go to a much higher concentrations, you are really distorting the system now. You get quite a diversification of solvation shells. You can maybe not even define the solvation shells anymore, because everything is interaction with everything. And there is basically little or very little free solvent, and that's beneficial. But what happens here is, of course, also that you're increasing the salt amount, and that means in the scale that we saw before with cost, salts are very costly compared to solvents. So this is a high-cost solution, so you have to bring some other benefits to it. But of course, benefit here, number one, is that you don't have free solvents, so you're improving the safety, right? But how can we understand that? And now I'm going to go a little bit deep onto what we're actually doing. So I had a very nice student who didn't really, he was not a chemist. So we thought that, oh, this thing with atoms, do we have to have them? Molecules, it's very complicated things. I like points. So he made these acetonitride molecules into central mass points. The target with this was really to see, can we study dynamics? Can we study ligand exchange in very highly concentrated systems where this is a little bit more tricky than in conventional electrolytes? Can we do that in a little bit smarter way? So we take some molecular dynamic simulations, and then we apply his idea of how to use forces and velocities in a random modeling way to see that, okay, can we see the ligand exchange in these specific systems? And then, if you bear with me a little bit, complicated slide perhaps, but what you get from this, if you're actually studying the radial force from what he's doing, his methodology, you can basically see how you have first and second solvation shells around the cation. So you see either the solvent, or if you're very highly ion paired, you also see the anions. And you see how they are actually moving back and forth. And this, of course, heat map. So you see the more intensity, the more ions or solvents you have around. But the really interesting thing is what happens when you're studying this as a function of cation or as a function of concentration. So you see when you're increasing the concentration now from 20 solvent molecules to 1 salt molecule down up to 5 to 1. So it's a very highly concentrated system. You see, especially for the sodium system here, that you have quite a lot of exchange. You have quite a lot of intensity between the solvent shells. And what does that mean? That means that you do have ligand exchange in a different way. And it also means actually that you have a more diverse solvation shell structure in these cases with sodium. And that is something that you actually translate to what you observe experimentally. You observe experimentally that you have a good power performance, and the good power performance comes basically from that you have an easier desolvation of your cation at the interfaces. And we can see also by the numbers that for the very highly concentrated electrolytes, you do have this. You have a very much faster ligand exchange, and that is actually exactly what we see with the kinetics and the power performance. So we get back to something that's really good. And can you quantify that? Well, I mean, this was some years back. This was 2020. But last year, Betar Gallant and MIT, they did some really nice thermodynamics of this ligand exchange by some microcalorimetry. So experimentally now verified. And her values, they are pretty close to what we have as well up here for the sodium system. So it's really fun to see that that could actually be done. And that's one way to think about it. But I mean, we still now did study it as separate solvation shells. But I did say that, do we really have that? Not necessarily. So the question is, if we take a little bit of a different approach, and this is a different PhD student project, we actually studied MD simulation trajectories, and we studied bond detection. And bond here is not the chemical bond, it's rather an interaction. So a lifetime of interactions here, basically saying that, okay, for a certain amount of time, these two species interact with each other. And then from that, you create what you call bond graphs. And then you boil everything down into these kind of different bond graphs. So you forget about the molecules again. I have a lot of physics students, so they don't like molecules, right? And then you do some statistical physics on that, those bond graphs. And that means that you can actually tell now what is living for how long time. And then as you have the molecular dynamics, you can also tell how is this transported, etc. And we actually created a company from this. That might sound very spurious, but we created a small company, and now we are actually helping battery companies in their R&D process to actually develop electrolytes a little bit faster. But that's a bit ahead of thing. What we do is basically that we can reveal the neighborhoods in a good way by these bond graphs. And we can also study ion transport mechanisms. We can study if this is a vehicular mechanism, that is that everything is moving along, nothing is really happening, or if there are non-vehicular mechanisms where you have a ligand exchange, you have a big rotation of a big cluster or something like that. We can see all of that, and we can study it as a function of concentration or as a function of system, etc. So that means that we see also things that you thought was actually not true. Everyone was saying that if you have a conventional electrolyte, it's always vehicular transport. There's very little contribution from other types of ion transport mechanisms. But in fact, we can see that that is not true. You do have other things happening as well. Not a major contribution, but it's always there. It's always there to some extent. And that means that you can actually study the ion transports. And then we actually created this company. I think this is something that, like an interlude in between the next part, what I'm going to talk. It's really fun to see that you can, from a PhD thesis, a student who has some drive, he's now the CEO of the company. We are 7 people employed. We're running with EIC money from accelerator program. And I know that, I mean, now during the 2 days here with the Scientific Advisory Board, we talk a lot about spin-offs and spin-outs. And I think this is a completely new world. I'm really much excited about that, just as much as excited for the things that I do in-house. And I think it's very fun the way that we can collaborate with companies, etc., in this way as well. But then, a different take. Going really to next generation batteries, calcium batteries. You see a lot here. You see Alexandre, you see Rosa, you see Damien, who was mine and Rosa's combined PhD student once upon a time. But what I'm trying to visualize with this is much coming from a review that we did, is that calcium batteries has potential. It has potential in the way that you can have both an abundant metal and you can create cells that deliver an energy density that can compete with the lithium-ion batteries. So that's really where you want to be. As I said, the context of it is really that you can do. Will we be able to do it? That we don't really know, but we're for sure trying really, really hard because we need that kind of chemistries around. So what are we actually doing? Well, we are trying hard, but there are reasons why we shouldn't maybe be so positive about it, because there are so many reasons why you should not do calcium batteries. And this maybe hinders the thought of some people. I mean, that was something that actually hindered a lot of people until Rosa discovered that, yes, calcium batteries are functional to some extent. But there are many things. There's passivation, there's lack of material, there is very little data there. You have very, very high demands of dryness. So there's a lot of things. But that also means that as a researcher, can we make it work at all? Really blue sky research, and that I think is very fun to make that. And I have tried to give you here now two different electrolyte approaches to calcium batteries. One is that we do a totally solvent-free, just along the lines that I talked about before, 100% salt, very expensive, but exploratory and has some promises. 0% salt, a totally salt-free electrolyte. And then you can say, yeah, it's a crazy guy. Yes, in situ formed electrolytes. And I will bring you to that a little bit in a moment. So one of my students, Johanna, who also was visiting here for a short time, we basically base her electrolytes on mixing salts together, getting the entropy of mixing, and getting them to be liquid, not at room temperature really, but for the ternary systems here, we're down at 54 degrees Celsius as a melting temperature. So you're actually getting now close to something that operates at room temperature, but is a molten salt, with all the advantages that can have. Well, it's not that we get like perfect cycling, but we can get something that operates, and it's like a proof of concept. And that is something that I take very much pride in, that we're doing that. Now we run it at 100 degrees Celsius just to get the speed up a little bit in the viscosity, because these are very highly viscous systems. But nevertheless, we actually can make it work. So that is something that one can say that, okay, we skip the solvents totally because they can degrade, they can be a risk or so. The other approach to do is that, well, if solvents degrade, let's use that fact. Let's think of solvents as a source for your electrolyte. So what we're doing here is actually basically that we're just making a solvent mixture, and then we're having it inside a cell, which is a calcium-calcium cell. And you see that you can actually cycle it. So there's no ions in the electrolyte initially, and that is the thing. That initially, so you have some reaction now between the solvent and the calcium surface, which then brings ions into the system. So to explain that a little bit better is actually this one, where we see that we're basically having, conventionally, we take a calcium salt and a solvent, and you make an electrolyte. Here you basically have what we call a precursor solution, and then you soak it in calcium foil, and you create a calcium electrolyte. And we can monitor that process. But the thing is that we need to balance very much what we're using as a system. So we have a borate system here, and the thing is, if we don't have both these components, we actually don't get it at all. We don't get it to cycle. And then a big thing that also Alexandra has been taking on here is that there is a certain role of the element boron for calcium batteries. It seems to be extremely instrumental that you have that present in the interface between electrode and electrolyte. Otherwise, you don't get it. So we can cycle cells. We can cycle cells with a rather low over potential. We can do it at rather low temperatures, like -10 degrees. It's not something that you would like say that, oh, hey, we have a great calcium battery, but it's like it's opening new venues that you can actually create an electrolyte without having salt present from the beginning. Because one problem is also that calcium salts are tricky. They are often impure, and you have issues with them all the time. So if you can avoid that step, that's fantastic, actually. So yeah, we don't really know where we're going in this map, but I think we're going in all places sometimes for certain technologies. And yeah, some stations might be more popular than others. That's what life is, yeah. And then future then, where does it lie? Well, I think semi-solid state electrolytes, solid state are very difficult to do. Some of you know that. I think that there is big promise in systems that are less solid, let's say. These in situ generated electrolytes, for sure. Then to go for fewer components. To make things very complicated, like today's electrolytes, where you have first a salt, then a mixture of solvents, and then maybe 10 additives to that, which is the commercial solution for a lithium-ion battery, is a very complex thing to do. And that in turn is very costly. So trying to reduce complexity instead of adding, I think that's a very good goal to have as a scientist, to simplify things, if possible, not too simple, as we say. And with that, I would like to thank the people who have done the work and the financing. Then, as usual, I'm trying to build what Rosa said. I moved to Uppsala quite recently. I'm building my group. I have loads of money, many positions out. So if any, and primarily postdocs looking for, but we're getting there. We're starting to get to a good team. And with that, I would like to thank everyone for listening and yeah, questions, whatever.
Thank you, Patrik, for this overview covering science, politics, strategy, whatever. So, floor is open for questions. And I may start. I mean, how much your strategy on ongoing a company with such a fundamental background is enabled by the fact that the Swedish ecosystem is different and the Swedish patent law is different from in other countries and so on, and how much can be translated to other countries? I mean, Spain is different in the level of funding and everything, but how much you think this, which is quite unconventional, I would say?
Yeah, okay, so maybe to explain the context is that in Sweden, the IP belongs totally to the researcher, whoever it is and wherever you are. So the university has no take. And that's also true for PhD student. If a PhD student discovers something in the lab, that PhD student has that IP. The university doesn't have it, the supervisor doesn't have it, it's the PhD student that has it. I mean, has it in the sense that it's yours to take care of. And that's also a limiting factor because you will also have to pay the patent. And if you're a PhD student, you might not have the funding for that, right? So then you would have to go to different support systems that exist in the university. And then I think the role of the university is really instrumental. And I would say that Sweden as a system, I don't really like this thing with how the patents, I think it actually hinders a lot of things because there is no automatic mechanism. But I was lucky to be at Chalmers, which really takes pride in being an entrepreneurial hub where we have many support systems. We have an entrepreneurship school where you can get a trained CEO. We have our own venture capital company inside because Chalmers is private, so you have many things. And that in turn helped a lot. But otherwise, I think that the system as such is not very good. And then, of course, it's up to the individual. So Rasmus, my former PhD student, he was working in a regular company for a year and a half, having one small kid and another one on the way. And then he said, well, I take the chance anyway. We're going to go for this. Brave decision, I would say. I mean, yeah, but he did it. And now we are surviving, let's say. we're not making profit, but hey, we are 7 employees and we're doing things. We have a customer base, and yeah, and we're doing a lot of good things, and we have developed a product. In the beginning we were only doing this thing that I showcase now, but now we can do electrochemistry predictions. We can do fast screening in a different way than we did before. Before it was much more to explain what is going on. Now it's more to screen away and to have a faster turnaround for our customers. And then some of our big customers, they go bankrupt, like Morrow last week. So that is unfortunate, but yeah. So I don't know I don't even know what the question was, but no, but I think there are probably elements of good things and bad things, but it's extremely rewarding if you can get a student or a postdoc to take on to do this thing. Now I'm going to start another company together with a former postdoc, and he's very much driving this as well. And I cannot drive it, but I think the young can because they have more energy. So yeah.
No, yeah, the question was about, because the mic was not on, that you really managed to create a company from very fundamental knowledge, and how was really this related to your ecosystem? And
yeah.
how
Okay. Yeah.
Translated?
No, I mean, the business side is completely different and no less important. And you have to have the students or the postdocs or someone who is willing to learn that side as well, and then bring in expertise, not be afraid to realize that you're a beginner, although you're really good on the research of your topic, but how to make a product of it, you are a beginner. Yeah.
Is there any other, yeah, Dino?
Thank you, Patrik, for the brilliant talk. I have first one specific curiosity about the solvation shells, if you could access them experimentally, for example, by EXAFS.
Yes, I think you could, but I guess that lithium and sodium are bad cations to look at the edges for, but yeah, I think you could. Because in principle, what you want to see is both short range and medium range order. So you want to see the whole convolution of the EXAFS, yes. Yeah.
And then I'm more generic. I'm curious to know, what are you doing with AI in your research?
Quite many different things. I have two students that totally focus on AI. One is doing fleet data analysis. So he's using petabytes of data, yeah. So he's getting information from two-wheel scooters that people are using in this. You have it in Barcelona, no? Yeah.
Yeah.
So he's getting information from a company of that, and then he's studying the aging of batteries and by AI basically. Yeah, that is one student. And I think that's with that kind of data, you need to use that amount of data. You need to use AI. Another student is doing something completely different. He's doing symbolic regression, which is a machine learning method that is not very common. But what you do with that is that you try to fit fundamental entities to the data, which means that you're developing equations. You're not fitting numbers, but you're fitting an equation. So what we're doing there is that the first thing we did was that we tried to develop a new equation for the ion conductivity of ionic liquids. So you select the target and then you do symbolic regression. And it's an uncommon flavor of machine learning. It's much less prone to overfitting. It brings you a lot of fundamental understanding, and I really enjoy working with. You need less data. Yeah, it's a fantastic flavor of machine learning, I would say. Yeah.
Other questions or comments from? Yeah.
Thanks so much, Patrik. I had a question about the electrolytes and their combination with calcium, because you said that there was some decomposition of the solvent during that process. So, I mean, I guess that's a massive opportunity because there are a lot of solvents. So, in general, in that specific case, I think it was DME, right?
Yeah.
So presumably this is a deprotonation of the DME somewhere on it.
Most likely.
Yeah. So, I mean, what bank of chemical knowledge is there about the reactions of metallic calcium in this case with different organic substrates? Because lithium chemistry, for example, is very well developed. As far as I know, calcium chemistry, organo-calcium chemistry is not.
No, exactly. That's part of the problem. And one part of the problem is also that you don't only need to predict what reaction there is, but you also need to predict, for instance, what is the solubility of these species that you actually react, because you want them to be non-solubilized, because otherwise you will not passivate the surface. And you want them to disrupt if there is a passivation layer already present. That should be disrupted. Then you should create a new passivation layer where through you can actually pass calcium. So there's quite a lot of different demands on that kind of reaction chemistry, because if it just reacts and creates a good compound, what you think is good, but it just solubilizes out into the electrolyte. And of course, that is also a property then itself of the electrolyte solvent. So it's quite complicated. And we've done some modeling of solubilities of different species in electrolytes and solvents, etc. But modeling solubility is actually a rather tricky thing to do. And even measuring solubility is not that easy as people think. So, and it's not that, maybe not the sexiest science to do to measure solubilities of species, but it's extremely helpful for us to have. But the database is rather bad, yeah.
And then just a very quick follow-up. So presumably you generate hydrogen in that process.
Yeah.
So,
which is bad. Yes. We don't. I mean, there are several other calcium papers where we know that there is hydrogen being developed. That doesn't stop them from publishing in Nature Materials. Let's put it like that. But yeah.
Maybe it's not, we don't have time to enter in this issue, but I would like to ask you, what is your opinion about the capability of Europe to integrate the scientific developments in an industrial battery product? What is the present stage?
No, I mean, this is something that troubles me. I can't say it keeps me awake at night, but I mean, that's something that I'm really on to together with some other entities in Europe. And we try to convince the politicians that you need to have a better support system. You need to act faster. You also need to act smarter. The problem is that the gap is getting bigger. At the same time, for every time we see that there is this new battery factory going bankrupt, as there is quite a bit of them, we also need in 2026 to look back to not 40 years, but 10 years, looking at 2016. Where are we today, 2026 versus 2016, and realize that we have quite a much better ecosystem anyway. So even if we have bankruptcies and we see that some of these large efforts are going down, I still believe that there is a possibility. Then the question is it going to be made in Europe or made with Europe? Are we going to create alliances with what we call friendly countries? Like I'm very much a proponent to do things with Japan, now that we have also a good collaboration on the Horizon Europe with Japan. Canada is another one of those countries where we try to stimulate interactions. But you cannot rule out the thing that you have to in some way think about how to interact with China. That is, yeah.
Good luck.
Yeah. Thank you. It's absolutely needed. No, it's very tricky. Yeah.
I think that in the interest of time
and my flight, I know.
To stop here, but thanks so much for the presentation and this enlightening discussion. Thank you.
Thank you, Rosa.
So now we wanted also to showcase the people that are currently part of ICMAB, the young people, the people that will celebrate ICMAB 50, 60, 70 years. So the ICMAB of the future, so future of ICMAB. So it's my pleasure to introduce Emma Ghiara, who is doing her PhD under the directorship of Teresa Puig on superconductor materials. So the floor is yours. Yeah, thank you very much.
So today I will present to you my work on data-driven screening of superconducting REBCO films via combinatorial inkjet printing. And I will focus mainly on the characterization part that I think is the most interesting for everyone. So the outline of my presentation basically consists in the 5 steps that we perform to fast screen the REBCO films. First of all, we synthesize precursor solution with different rare earths that then we use as ink in an inkjet printer to deposit combinatorial samples. Afterwards, we grow these samples through the TLAG process in order to produce the REBCO film. And finally, we can perform a series of automated characterization techniques in order to build a large data set and to finally optimize the final material. So the precursor solutions are synthesized here in-house, and they may contain different types of rare earths as yttrium, gadolinium, or erbium. And additionally, they may contain nanoparticles. An ejectability study was conducted in the beginning of my PhD in order to be sure that we can use this solution as ink. And this is mainly given by the rheological properties, so viscosity, surface tension, and density. We can see here that this ink remains stable for at least 2 months, so it's good from a stability point of view. So then the deposition happened through an inkjet printer supplied by Microdrop Technologies. And so we supply a combinatorial design to the machine via bitmap image. So basically, in the image, we have different pixels which codify for the ejection of a specific drop from a specific nozzle, which contains different solution. So once again, after a long optimization process, we are now able to deposit combinatorial samples in less than 10 minutes, in which different precursors directly mix on top of the substrate. After the deposition, we then produce the REBCO film through the novel TLAG process, which has been developed in the group in the past 15 years. And it mainly consists in 3 steps. First, there is a pyrolytic process in which we remove the organic part, and we end up with a nanocrystalline precursor of K-PeRO, barium carbonate, and rare earth oxide. Then, in the second heat treatment, is when the REBCO crystal actually form, and through the formation also of a transient liquid of barium and copper. This process is the real key that we are trying to investigate the most, since it is highly dependent on pressure, temperature, and composition. Finally, we perform also an oxygenation process in which we convert the REBCO film in a real superconducting material. So once we have the sample of a REBCO thin film with a gradient in rare earth composition or nanoparticle concentration along the x-axis, we can perform different type of characterization, different type of automated characterization. Here in ICMAB, we can perform interferometry maps in which we can have a thickness map of the sample in less than 10 minutes, but we can also perform automated characterization of the rare earth composition via EDX in the SEM here downstairs, which is a really tricky measurement, since to detect the rare earth in the thin film is not so easy. It lasts more or less 48 hours, but luckily, being automated, we can perform this during the night. At the same time, while the EDX is running, we can also acquire the SEM images for doing surface morphology analysis, although this is not always so straightforward because the focus needs to be always corrected manually. So this is a little bit, we can still improve regarding the automatization of the surface morphology. At ESRF synchrotron in Grenoble, we were also able to perform X-ray fluorescence maps with a micrometer scale resolution, which allowed us to verify the fact that the rare earth truly mix inside during the deposition at a micrometer scale. And also we were able to detect the copper oxide secondary phases that we have inside the film. And this is really helpful for us because at the same beamline, we can also perform X-ray absorption spectroscopy. So to be able to detect copper phases, and so well, no, I don't know this. So to be able to detect the copper phase and separate it from the REBCO phase, we can perform SAS spectroscopy on a region that we are sure it's pure REBCO film. At the same beamline, with the same strategy, we were also able to detect the hafnium concentration in a nanocomposite sample, which is directly correlated with a nanoparticle concentration. And this was really tricky to achieve since the atomic percentage of hafnium, it's really little in the sample. So this verifies the fact that we can also produce combinatorial nanocomposite gradient. In ALBA synchrotron, instead, we can perform XRD maps to verify the crystalline quality of the material, for example, by following the intensity of the REBCO 005 epitaxial peak. But we can also detect the possible secondary phases that we have, mainly copper, but also rare earth oxide or the 211 green phase. At last, with our collaborators at Kyushu University in Japan, we are also able to measure the superconducting properties of the film with an extremely high resolution, which allows us to directly see how the different composition affect the final superconducting properties. For example, we can even see the effect of nanoparticles in the material, which improve the vortex spinning. So at last, from all these property maps, we can generate a property correlation matrix, which has the aim to identify the correlation between different properties. For example, here I have highlighted the fact that the rare earth distribution is highly dependent on the X location, while it's almost independent on Y, as expected by the combinatorial design. But also we can see that the superconducting properties increase with gadolinium content in this specific sample. So in conclusion, we built a robust methodological framework to efficiently study the TLAG process parameters through the implementation of different characterization techniques. Thank you for the attention.
Thank you very much, Emma, for such a nice overview of your tough topic. I would say, any comments, questions from the audience? I have one question out of ignorance. I mean, you mentioned at the beginning when you make the deposition of your layers, you measured that. We optimized it or we developed. I mean, I guess there is a lot of work behind this optimization, behind this developing a reproducible process. So can you comment how?
Yeah, it was a really long.
Which were the main bottlenecks?
So it was a really long optimization process because the inkjet printer has like the nozzle tip is extremely small, so there is always the danger of having evaporation at the tip of the nozzle and then it's clogged. So the main idea was to change one of the co-solvent in the ink in order to have a much lower boiling point, which seems counterintuitive because the evaporation is faster, but this also allows us to print extremely fast, while before it was maybe 2 hours to get one sample. So that's that.
Thank you. Any other comments or questions from the audience? Yeah.
One curiosity is, so your film, well, when in this image, for instance, the film is continuous. I mean, there is a connection between regions of different composition.
Yeah.
To what extent you don't have interdiffusion? Because when you have a gradient, you promote the chemical diffusion, especially at high temperature. And why not making separate, let's say, droplets that are not in contact to avoid any diffusion?
No, we want diffusion. So
you want diffusion?
Yes. So
I understand.
So this is what we give to the printer. And so the idea is we can only eject 1 drop per location, because otherwise we would not have homogeneous thickness of the layer. So we cannot print the 2 drops on the same place. But we still want a linear gradient in rare earth composition. So
this by diffusion.
Yeah, we achieve that by diffusion. And even by TEM, we prove that the diffusion is really good. I mean, there is no cluster of one rare earth compared to the other.
Well, thank you very much. Let's thank Emma. And now I'm handing over to Mariano as the next chair.
Okay. So very brief introduction. It's a great pleasure to see Paolo again. He was part of ICMAB. He did his PhD here with Ricardo Rurali in a project that I was also involved. So we were good collaborators in the topic of thermal transport in polymers. So I'm really curious to see what he's been doing since. So Paolo, good to see you.
Thank you. Okay, can you all hear me? Yes. Also the people online, I'm guessing. So I'm Paolo. As you can see, I'm proudly wearing my 35th birthday of ICMAB shirt. So this is precisely, I guess, quite precisely 5 years old shirt. So that's a feat by itself. So this is a bit now intimidating to me since I've changed my field of work, actually, Mariano. So I have nothing new to tell you, because my audience is now mostly young teens since I'm teaching in high school. So, but yeah, so this will be like a very condensated talk about my work here as a PhD student with Ricardo at ICMAB. So thank you for having me. So yes, my work was about organic semiconducting polymers, especially related to thermoelectric applications. So first of all, for the people who are not familiar or just who need some reminding, what is thermoelectricity? Thermoelectricity is is this phenomenon where we are able to generate a voltage from an applied thermal difference, and this is governed by several parameters like the Seebeck coefficient, so the ratio between this created voltage and the temperature difference that is applied. And we measure the efficiency of thermoelectric generators with this dimensionless figure of merit, ZT, where we have the electrical conductivity, the Seebeck coefficient squared, temperature, and the heat conduction, the thermal conductivity, K. So a good thermoelectric generator must exhibit large S, of course, large S and electrical conductivity, and low K. So about doping in organic semiconductors, so we call the numerator of the ZT power factor and is this factor. And so I say it increases with the square root of the electrical conductivity and not linearly because the Seebeck coefficient is also affected by the electrical conductivity negatively, unfortunately. So we all remember that the electrical conductivity is given by this expression where we have the charge carrier density, elemental charge, and mobility. But yeah, S is inversely proportional to the charge carrier density. So we need to improve mobility to improve the power factor. Whereas total thermal conductivity is given by the sum of an electronic contribution and a lattice contribution. We normally use the Wiedemann-Franz law to connect the electrical conductivity and the electronic contribution to the thermal conductivity. However, this does not hold for a large range of organic semiconductors. Eventually, if we want to increase the efficiency of thermoelectric generators, we might think to increase the electrical conductivity, but this eventually will will also increase the thermal conductivity due to the increased electronic contribution to the thermal conductivity. So actually reducing the lattice contribution to the thermal conductivity is a good strategy to lower to shift the maximum efficiency to lower electrical conductivity. So our work, mine and Ricardo, was mostly focused on PDOT PSS. These are the chemical structure of these molecules, and I worked mainly with molecular dynamics. So the way in which we calculated the thermal conductivity, the lattice thermal conductivity in these systems was with this technique called approach to equilibrium molecular dynamics. So this consists in just creating a simulation box, dividing it into two halves, and setting a step-like temperature profile. For example, we used to set one half at 400 Kelvin and the other half at 200 Kelvin. And so create a delta T of 200 Kelvin, and then let the system reach equilibrium. While the system reaches equilibrium, we monitor the average delta T, which is the difference between the average temperature of the two regions. And we are able to extrapolate the lattice thermal conductivity from the exponential decay of this of the average delta T. And so what we found, we studied PDOT in its undoped and its doped form. So the undoped is here in these graphs with the blue line. We found some very well-known results for the case of undoped PDOT, which is that the lattice thermal conductivity increases when we also increase the average length, the average molecular weight or length of the chains of PDOT. And we found that there is also a weak negative correlation between the density and the average molecular weight. So as we consider longer and longer PDOT chains, also the density starts to decrease, even though there is weak correlation. And when we consider doped PDOT, we notice that there is so this is the red line here. The K is generally increased, but there is not really an increase. So the K is not increasing with respect to the to the average length of the chains. Instead, there is sort of a peak around here for intermediate chain lengths, and then it's starting to decrease again. And this is eventually just due to, we can also see that the density is quite evidently decreasing with the average chain length. And this is ultimately due to the aromatic to quinoid transition that P-dot undergoes upon doping. So when P-dot is undoped, it has an aromatic structure. When it's doped, it goes to quinoid, and this makes the P-dot chains stiffer. And so ultimately, this makes the distribution of the P-dot chains a little bit more difficult when it's longer and longer, because they are like uncooked spaghetti, as Ricardo likes to use this metaphor. And the thermal conductivity is negatively affected from this. The green triangle that we see here is just one single sample of P-dot, where we have included the polymeric counter anion, PSS, and it causes a sharp increase in K. And we were able to confirm it also by calculating the thermal conductivity of PSS with just a positive sodium counterion, which is 0.25 watts per meter Kelvin, which is outside the graph, so much higher than all of this. So PSS is actually what is destroying the thermal conductivity of this kind of systems. We also measured the X-ray diffraction peaks of undoped and doped P-dot. So here is the undoped, and we measured a pi distance of 4 angstrom, and upon doping, it shifts to 3.6. So this has it doesn't really have implications for thermal conductivity, but it probably does for electrical conductivity, since it could increase the electron tunneling probability. We also studied another kind of system. So the system that we were considering till now was amorphous P-dot and P-dot PSS. In this case, we also studied crystalline nanofibers of P-dot, and we created this by basically replicating P-dot chains in 3D space. And you can see an example here. And there are two different cases. So a case with van der Waals gaps along the backbone direction, like we see here in the C figure, and without van der Waals gaps along the backbone direction. And we wanted to know if we could leverage anisotropic transfer properties to suppress lattice thermal conductivity. During this investigation, first of all, we found out that there are two possible lateral registries for P-dot chains. One is through H bonds between dioxyethylene groups, like you see here, and the other one is electrostatic interaction between oxygen and sulfur in this way. And this also slightly affects thermal conductivity, whether the lateral registry is in the first or the second. What we found was a little bit counterintuitive, that the backbone is not the most conductive direction. It only takes over if the nanofiber is long enough. So this means that in this kind of system, interchain transport is limiting the thermal conductivity. And whereas, yes, pi direction is the least conductive. And we were also able to extrapolate the thermal conductivity for like infinitely long chains without van der Waals gaps at around 2 watts per meter Kelvin. Whereas when we consider the van der Waals gaps, it goes down to just 1 for an infinitely long nanofiber made of pido chains of 6 monomers. So as a summary, we found that doping generally increased the lattice thermal conductivity, but interchain transport is hindered for long chains due to the increased stiffness associated with the quinoid structure, and that the addition of PSS contributes the most to the increase of lattice thermal conductivity. Whereas in this system, the p-dot crystalline nanofibers, we see that thermal anisotropy can actually be leveraged to suppress lattice thermal conductivity to some extent if we are able to control the aspect ratio of these fibers. So during my PhD, of course, I was part of the apparatus network, and I collaborated with some people in Sweden, Linköping with Igor Zazulenko, and at Hot Disk with Besira. And so thank you to all the people who made my investigation, my study possible. And yeah, thank you. Happy birthday, ICMAB.
Well, we are a bit late.
Yeah.
So is there any urgent question, I'm afraid? I mean, you're going to stay here for the day? Yeah?
Yeah.
Okay, so you can catch with Paolo maybe over a coffee break, if that's okay. And then we pass to the next talk. Sorry. Okay, next talk is a plenary talk by Professor Jenny Nelson from Imperial College, London. She performed her PhD also in the UK, in Bristol, in a slightly different topic. And then she moved to photovoltaics, and she's a world expert on photovoltaics. She has written the most, probably the most cited book on photovoltaics, the physics of photovoltaics. And her research combines both theory and experiment. So it's very is one of almost unique as a single researcher that can do both things simultaneously at such a high level. So it's a really. I was thinking, just because today's anniversaries, I think Jenny and I know each other from 25 years ago. So that's a bit of time, I guess. Yeah. So it's a great honor and pleasure to have Jenny Nelson here to give us a plenary lecture.
Thank you very much, Mariano, for the introduction, Rosa, for the invitation to come here, and I'm happy to be here on the 40th anniversary. Can I remember the occasion? I remember he had very long hair. I can remember that, and it was definitely 2021. So, the topic of I'm here, of course, partly in my role as the High Chair, CSIC High Chair from 2024, and that has arisen from a long-standing collaboration with ICMAB, largely via Mariano Campoy, but now also through other researchers here. So, I will start. Maybe just picking up the point that Patrik made at the beginning of his talk just now, which is that we're witnessing and will see a growth in the electrification of different forms of energy, and that's necessary in order to minimize carbon emissions. And along with that growth in electrification, there will come the integration of renewable generation with a lot of different applications, not only with electricity as we normally consider it, but also with other sectors like transport, with buildings, with agriculture, and so on. And so a point to make, even if I say nothing else, is that this transition will require materials, and this transition creates opportunities and needs for new materials and materials development. Now, I'm interested in photovoltaic energy generation, and a lot of this increase is going to come from photovoltaics. And traditionally, photovoltaic generation is provided by solar cells, most commonly made from silicon, where you have basically a process where a photon comes from the sun. It's absorbed in a material which has a semiconductor material that has a band gap. And when the photon is absorbed, it promotes an electron, and this device this material is capable of separating the photoexcited state into an electron and hole, and then in separating the electron and hole and giving them a direction so they travel through an external circuit and can do electrical work. Most often it's done with silicon. We're doing it with organic semiconductors, so molecular electronic materials, and there's various reasons to be interested in these, amongst them the sort of basic scientific question. And when you try to do the first thing, which is to convert your photoexcited state into electron and hole in an organic semiconductor, that is problematic because the excited state is very tightly bound in that material and is more likely to decay back down to the ground without separating. So if we want to actually drive a photocurrent, we have to get past that problem. And the way to do it is normally to use a combination of materials that creates an interface or a heterojunction where you have a driving force to separate this photoexcited state. So when you come with a photon, the electron is attracted towards the other material into what we call so I'm looking for into what we call the charge transfer state. And from that and from that state, so the electron. So I was just looking for a pointer here. Top one. Okay, got it. Thank you. Sorry. Yeah. I'm trying to drive it. So we have a transition from a photoexcited state to a sort of charge transfer like state where the electron and hole are in different sides, and that then can generate fully separated charges, and so generate a photocurrent and a photovoltage at the same time, and those processes compete with different backward processes. That's the idea. That has been the idea since the sort of inception of molecular photovoltaic devices. So when Mariano and I met, it was probably just before the beginning of this. And then over this period, and probably no consequence whatsoever of anything we did, the efficiency has risen to now exceed 20%. And that has been a consequence largely of the development of new materials. First of all, the development of conjugated polymers, which had improved properties, and more recently, the development of molecular acceptor materials, which have very interesting properties, and I will focus on them later on. And now efficiency has exceeded 20%, which is it's interesting because it was considered when we started impossible, and now it's completely possible, and it's not good enough. But that's, that's how life goes. No reason to stop trying now. One of the things to comment about these systems as material systems is they're actually quite complex. So you have two different materials with different electronic properties. And of course, different materials will come with different material properties that will influence the type of structure that they form. Microstructure is very important. There are many things to think about, but it's actually very surprising that these materials can work as well as they do. I mean, we consider that, the best efficiency of a silicon solar cell is 26%. Gallium arsenide can make 28, 29%. For this sort of messy materials to make 21% is quite surprising. And so it's a nice challenge to try to understand and see how we can push things better. So if we think about the things that are kind of accepted about these materials, and it's sort of convenient to think about it in terms of a competition between these processes of the separation of this exciton into charges and the recombination events that compete with that, what do we know? So what is pretty much accepted is that we do need some kind of heterojunction to split the charges. Once you have a heterojunction, you can generate a photocurrent, but then you have a competition between photocurrent generation, for which you would like to have a small offset, a large offset, and voltage generation for which you would like to have a small offset. And so there's a compromise there. We also have the fact that the recombination is relatively strong in these materials for reasons I'll comment on in a minute. And that's kind of understood. And then, to finally generate the current from the solar cell, we also care about the electronic properties of the materials and the interfaces and so on. So what I'm going to do in this talk is kind of talk about, I suppose, the different aspects of this question and look at what we understand and what we think the challenges are that remain to improving performance. So I'm going to start with this sort of the question about recombination and what limits it. And with the solar cell, you want to generate a current and a potential at the same time. And the maximum that potential can be when you illuminate your solar cell with what we call a standard sun is the open circuit voltage. And that open circuit voltage will be limited by the band gap of the material that you use, and also by the ability of that material to convert the photoexcitations into current. And if there's an efficient loss pathway where charges are recombining through defects or whatever, then the voltage is limited. And so the size of the voltage is kind of a reflection not only of the band gap, but of the strength of the recombination processes in the material. And we can quantify it by working out what open circuit voltage the material that we're using should have if it were working perfectly, which is in what we call the radiative limit. And we find that we can work out, we can look at the difference between the actual voltage and that perfect value, and that should be related to the relative efficiency of radiative and non-radiative recombination processes. And if we look at this for the case of organic solar cells, that gives us data like these blue dots over here. We can see that this value, this loss, is larger than it is in the bests of other types of solar cells. So, for example, gallium arsenide has a very small number because it's a very radiatively efficient material, at least in a single crystal. Silicon is pretty good. Perovskites are also pretty good. And what's the reason for that? And this is a fairly fundamental reason. So we can describe these processes quite well using tools from physical chemistry, where we look at this transition between the excited state and the ground state. And we describe the rates with Marcus Levitz-Jortner, sort of semi-classical rate theory. And the point is, so we can write down the rate of radiative, non-radiative, and radiative recombination and work out the ratio between them, and then work out what the open circuit what this voltage loss should be. But the point here is that the non-radiative decay, this rate is quite fast. And that rate is quite fast because the excited states can be, their energy can be dissipated to ground relatively efficiently through quite high energy vibrational modes of the material. And those high energy modes are coupled to the electronic excited state. And that means that they can dissipate the energy relatively easily. And that's something when we look at the origin of those vibrational modes, so they're connected with the pi conjugated system, with the carbon-carbon double bonds that sort of underlie all organic semiconductors, it's quite hard to eliminate them. And so then that looks as though it may be a showstopper, and it's certainly part of the reason why these non-radiative voltage losses in these materials are high. However, when we have a sort of theoretical description, you can kind of work it out, and then you can see what your losses are a function of. And they don't depend only on the energy of these modes, but also depend on other factors. I mean, so the coupling to those modes is represented by the reorganization energy here. But there are other things like that matter as well, like the brightness of the state, the dipole moments, the energy of the state, and so on. And with a framework like that, we could then make some projection about where efficiency might get to. And this is a projection that we made in 2018. It was too pessimistic because since then the limits have been passed. But these were limits that we sort of made thinking about what we thought would be the most optimistic value of one or another parameter for the material. But it's really just kind of like first step towards trying to work out where we could go with those materials and some sort of ideas how to get there. So I move on then to the next question about photocurrent generation. And if we only sort of think about the last topic, which is the voltage. So the voltage is going to be higher, the higher this energy of the charge transfer state is, and that means the smaller is the offset in energy levels between the frontier molecular orbitals of the donor and acceptor. So if you have a given set of materials, and if you could play with the offset, then if you just think about voltage, you want to have the smallest possible offset, and that should be the best condition. But if you look at experimental data, when the offset becomes very small, then although voltage may become high, we lose the photocurrents. We lose the ability to drive a photocurrent across the heterojunction. And that's just some data here showing that when the offset becomes small, indeed, open circuit voltage becomes higher, but we begin to lose the current and we lose the fill factor. So we need to not only understand these losses that occur through recombination at open circuit, but we need to understand what is driving photocurrent generation and how big a driving force we need. And so to do that, we needed to consider not only these recombination rates, but we also need to consider the whole process of photocurrent generation. And we did that by making a device model in which this sort of physical chemistry part is embedded into the equation so that at the same time we could think about what we generate from our semiconductor device and what parameters that control these transitions at the interface, what effect those parameters would have on the outcome. And then when you have a model like that, you have very many parameters. And when you have very many parameters, then it's very hard to find the unique set of parameters that would explain a single piece of information. So for a solar cell current voltage curve, that actually is very, very easy to fit. There would be many ways of doing that. And so if we want to really understand the system, then we should have different types of experimental data to fit with the same model. And that's the approach that we take. There's an example here where for a particular set of materials, we measured not only the current voltage curves, but we measure the light emission from the devices. These are systems with different offsets. And we measure the photo and electroluminescence and the external quantum efficiency photocurrent. We look at the transient absorption kinetics, and we look at the optoelectronic dynamics. And then with that same sort of model, we fit all of those. And having fitted all of those, we could then project what should the current voltage curve be like. And the model would indeed project that as the offset becomes smaller, the voltage should become larger, but the current and the fill factor, the shape of the curve, are compromised. So that's a tool that's useful. And having got the tool, that then allows you to kind of ask questions about what if. So for example, we could now sort of revise our map of power conversion efficiency as a function of band gap and look at it as a function of some parameters controlling this sort of competition of both what happens at the interface and what happens in the device. And for example, we find that if we were to change the lifetime of the photoexcited state, if we make that longer by reducing the high frequency reorganization energy for the exciton, that allows our power conversion efficiency, higher power conversion efficiencies to be reached at a smaller band gap. So that's a good thing. The comparison here, so this black curve here is what you would have in the absolute radiative limit. And these green lines are the projection for the molecular materials. And we see that the projection crashes at low band gap. And that is because of this sort of back of when the band gap becomes small, we start to squeeze the driving force that we can have to separate the charges, and we start to feed the excitations back into the CT state, back into the local excited state, and the excitations go to ground. So it's kind of reflecting that competition that influences the behavior of the devices in real life. So this is a tool, and it allows us then to kind of look at what could be possible. It also allows us to kind of analyze what has been done. And just as a kind of, I suppose, reflection or sort of semi-validation of the model, I've got here some data representing the performance of different molecular solar cells, their band gap and their power conversion efficiency. And we can see that they're sort of up against a wall. And the more recent materials are represented here around about this big cluster of reports around about 1.4 electron volts going up to 20% efficiency. They're kind of consistent with this limit, but it's clear materials are getting better. This would suggest in terms of their excited state properties, and I think that is also true as time goes on. So what the model does is it allows us to explore the impact of material parameters. And one way that we've used it recently is in a collaboration with ICMAB, with Mariano. So his group has introduced the concept of this rainbow solar cell, where you have a lateral multi-junction solar cell, and you split the solar spectrum into different intervals by with some optical device. And then having done that, you would have the opportunity to individually optimize solar cells of different band gap and to convert those slices of the solar spectrum as efficiently as you can. And so we could use our model to see what could be possible, not only considering the most basic type of solar cell, but considering, the most sort of basic model for limiting efficiency, but actually considering the molecular properties of the solar cell. And my colleague Yolanda has done this simulation for a recent paper with Mariano and his group, looking at what might be possible if you could optimize all of the molecular properties within reasonable ranges. So I commented that the efficiencies had been increasing rapidly recently because of using a variety of new acceptor materials that were introduced. And these are really a set of, probably a chemist would call them oligomeric molecular materials, relatively high molecular weight. And they have there's a wide variety of them, of course, because different building blocks can give you different properties. And the ones that work well in solar cells are kind of characterized by, they tend to be flat, and that allows them to pack rather efficiently. So you tend to get reasonably good crystalline structures formed with good sort of pi-pi interactions between neighboring molecules. They tend to have rather favorable excited state properties. So the exciton lifetime might be a nanometer or so. That would be very favorable compared to a conjugated polymer, typical conjugated polymers. And therefore, they will have long exciton diffusion lengths. And another sort of important thing is if we look at their optical spectra, you tend to see a very strong redshift in the solid state compared to in solution. And that's a signature that there's quite strong electronic coupling between the molecules, leading to delocalized excited states. So there'd be strong, so we expect that there should be strong coupling between different molecules. So if we look, so I'll now comment a bit on a recent study. This was again a collaboration with ICMAB, where we were interested in how does the chemical structure of the acceptor material control the behavior? What's special about the best of the new materials? And so as part of this, we looked at photocurrent generation at heterojunctions between our acceptors, so we call them NFAs, non-fullerene acceptors, and with different ionization potentials that present a different offset next to this copper thiocyanate donor layer. And we look at the quantum efficiency, and we see, not surprisingly, as we make that offset larger, the quantum efficiency gets better. We can plot that. This is exactly what we've seen before, that as this offset gets larger, photocurrent gets larger until it kind of saturates. But the interesting thing here was when we changed the material family, so these are the ITIC material family, but when we go to a Y material family, including Y6, which is one of the best performing materials, and other analogs, we see the same behavior, but it kicks off earlier. So it looks as though the Y family is able to generate photocurrent at a smaller offset than the ITIC family. So that's something interesting and something that we wanted to understand. And we couldn't really understand this with any of the types of models that I showed before, where we have transitions, we have decays, we have charge separation, thinking about a single molecule. Because it's not clear if you just look at, I mean, the diagram already tells us, it's not clear if you just look at the energy levels, why one material family behaves better than another. So we needed to build a more detailed model which would take into account the ability of these excited states to delocalize over multiple molecules. And so we build this model considering that we have some structure in which we sort of coarse grain our molecular structure into a lattice or an assembly of points. And then we set up a tight binding Hamiltonian where we allow the sites to interact with each other. So an exciton on a single molecule can interact with excited states localized on other molecules, both forming neutral excited states and charge transfer excited states. So we have a Hamiltonian, two-particle Hamiltonian in an electron hole basis. That means that we have both excitons and charge transfer states in the same model. And then once we know the couplings, if we know the positions, we can work out the couplings between different molecules. And then we could solve that Hamiltonian to find the energies of the states. And we can also look at the character of the states. So the states which are excitonic will have an energy somewhere. And then some of the states will have charge transfer character. And then we can classify them in terms of excitonic, charge transfer, charge separated states. Having got the states, we can then model the transitions between the states, and then we could get information about populations as a function of time in a transient experiment, and then project things that we might measure, like absorption or emission spectra, or the efficiency of photocurrent generation as a function of offset. So this is kind of a framework. It's quite complicated, but it allows you to probe many things. And when we apply it to the question of photocurrent at a heterojunction, we look at what is the efficiency of charge pair generation as a function of this driving force, this offset. And then what we're interested in is what if we change some parameters associated with the molecules, how would they affect this? So the thing that we saw when we compared ITIC with Y6 was we see this trend that the photocurrent turns on as the driving force goes up, but it turns on earlier with Y6 than with ITIC. And what could be the reasons for that? And so the model is telling us that one reason, and this wouldn't surprise anybody who works with these materials, one reason would be if the exciton binding energy was smaller. And then maybe less obvious things. Another reason can be if the electronic coupling between neighboring molecules is larger. And another would be if the reorganization energy, in other words, if the reorganization energy of the exciton is smaller. That would mean its lifetime would be longer. And if we look in literature and we make a comparison between the Y6 family and the ITIC family, it's not, to my knowledge, completely obvious that there's not known, I would say, not well known if there's a difference with the exciton binding energy. But we do know the electronic coupling is stronger in Y6, and we do know that the exciton reorganization energy is smaller in Y6. So we can rationalize what's going on in terms of the material parameters. This then raises a question. So this can kind of help us to understand why with these new family of acceptors, we're able to get a good photocurrent quantum efficiency at a relatively small cost in terms of this offset. But it also allows us to ask a different question, which is, could it be possible that these solar cells made with the new acceptors are working very well actually because you can generate charge pairs directly in the acceptor material? And I raise that question because it's been raised a lot in the literature, and this tool allowed us to look at it and find out, could that be the case? And basically we concluded no, and I'll try to explain why here. So we try to find, with the model, we see what photocurrent we generate. We can also see where those separated charges were born. Were they born just in the acceptor, or were they born because of exciton dissociation at the interface? And the data on the right are telling us that most of the time, if we ignore the blue curves and just think about the green ones or the orange ones, the crosses are showing us this is the photocurrent that was born at the interface. And then the dots down here, this is the photocurrent that was born in the acceptor alone. And you can see it's negligible. Most photocurrent comes from exciton dissociation at the interface, except if you go to conditions where the exciton binding energy is very small, and then it's easier for the exciton to break up in the acceptor domain itself and generate some significant photocurrent there. But if that were the case, other behavior would be different. So we think that's out of the regime of properties of materials that we have at the moment. So then you can see what, I'll skip that. So I think I'll make this the last topic here. So we've been looking at these heterojunction materials and trying to build a framework where we could explore what properties influence the heterojunctions. And one of the problems with the heterojunction, well, there are several problems, but some of the problems that I've mentioned that the heterojunction creates an interfacial state where recombination to the ground is quite efficient. We also have the problems that I've alluded to at the beginning. You make this mixture of materials, they're soft materials. There's nothing really, they're not very strongly, the structure is not very strongly directed. And if you give it some time, if you give it some thermal energy, it may disintegrate over time, and that's actually one of the important degradation mechanisms. And then, of course, we have the fact that the arrangement of our donor and acceptor molecule next to the interface, that's probably going to be very important in controlling the energy of this state. And yet it's not that well controlled. So we may have different arrangements of our donor and acceptor next to the interface, and they may present different energies, and that would introduce disorder. And so I used the model I introduced earlier to look, actually Yolanda did it, to look at the effect of increasing the disorder in the energy of the interfacial state, and we can see that it compromises efficiency, so we would like to reduce it. And one way to do that, that we've been looking at, is to work with the same molecular units, but rather than having a mixture of one semiconductor and another one that's sort of created from solution processing, we looked at materials that were made by collaborators in China, Jimin and his group, where the donor and the acceptor are covalently bonded together into a block copolymer structure. So that the sort of the way in which the donor and the acceptor interact is actually chemically controlled. And then we're interested in whether that might lead to improved performance. So when you do that, and if you then make a comparison between the solar cell made from the donor and the acceptor mixed together, we find that it tends to reduce, for the same materials, it tends to reduce current, increase voltage, and the efficiency might either increase or decrease. So that was a question for us to look at. And we did. And we found that the voltage is, I mentioned that the voltage tends to increase. And we see that that's associated with a somewhat smaller voltage loss. The current tends to decrease. That's reflected in a smaller external quantum efficiency. And then to try to understand what could be leading to that from a sort of molecular level, we did some calculations on the nature of these interfacial states that would be formed between the donor and the acceptor. And we were looking at different components that would produce different offset sort of arrangements. But what we can see is if we compare a combination of materials in the block copolymer structure compared to in a bulk heterojunction structure, that the interfacial, the kind of through bond excited state tends to be larger in energy, and the charge transfer like state is more excitonic than in the case if you had the same materials and they're interacting through space. So it sort of rationalizes why the CT state is more strongly coupled and larger in energy. That rationalizes a larger voltage, and it also rationalizes the idea that there's a smaller driving force for charge separation. To sort of push it to the edge, we then thought, okay, let's make a comparison between these block copolymers and exactly the same materials, but in a polymer-polymer arrangement, and see what happens now that we know how to work out the offset. How does the photocurrent depend on the offset? And in fact, we find that it looks, from what we've done, as though there's not an advantage of the block copolymer arrangement over the polymer-polymer arrangement, because in the end, they get limited. So it's a bit disappointing, but that's what we got. And it's kind of telling us, yeah, we still need a bulk heterojunction to get a high photocurrent efficiency. So I had a couple more slides, but I've got a way to jump to the end, but I don't think I can operate it from here. So I will just have to jump over the slides. It was really, I'll just introduce here so you can see the context that going back now, this is more than 10 years. This is another collaboration we had with Mariano when he was here at ICMAB. We were interested in using, one of the reasons to be interested in molecular electronic materials is that unlike any other semiconductor material, you can design the material in order to absorb light in the infrared and transmit in the visible. And that, of course, is very interesting for applications, amongst them the idea of sharing the solar spectrum between photocurrent generation, exploiting the infrared, and photosynthetic work, where you use the visible part of the spectrum. And this is just what I feel I'm running out of time, so I don't want to say a lot about it, but we were developing, I know this is an area of active research in at least in Mariano's group at the moment, to look at the best materials that could be used to combine those functions of plant crop growth and photovoltaic generation. So we have quite a nice model system where we're looking at these photovoltaic polytunnels and working out what is the, we have an optical model, we have an electrical model, considering photovoltaics that are stretched across this curved geometry, and we validated it against some experimental data, and we can, sorry, I've come to the end rather suddenly. Thank you. Sorry. So to conclude, most important thing, I think, no matter what area you work in, is we are in the middle of a transition in the energy system that involves a great increase in electrification. Solar is going to be probably the single most important source of electricity within a decade or two. And that will create a need to electrify many functions, and that will create the need for the materials that allow that integration to happen. And amongst the type of materials that can be used as part of this transition and for certain applications are soft or organic electronic materials. I've been talking about those. The devices have exceeded 20% in efficiency, which is fantastic, but not fantastic enough. And then we've been looking in depth at how the properties of those materials sort of both enable and limit the process of photocurrent generation. So I stop here. I'm going to. Okay, I have got a slide that thanks people. Yes, thank you. Thank you to my collaborators in Imperial. Thank you to Mariano. Thank you to other collaborators and to you for your attention.
Thank you very, very much. Jenny, it's time for questions. A few questions before coffee.
Thanks so much, Jenny. I had a question about the polymer system that you described, because your kind of message was that there's no advantage of the block copolymer with respect to the polymers. But I mean, in a material sense, there is, because in the block, you wouldn't have phase separation.
Yeah.
So, I mean, there's always this trade-off, isn't there? I think between, and you mentioned interfaces as well. So I wonder if you could maybe develop that idea a bit and think about what could be done.
So definitely the block copolymers have shown, I mean, one of the reasons to develop them is exactly what you say, that you try to reduce disintegration of the materials, and they do show better lifetimes, particularly under those conditions of higher temperature that would lead to segregation. So I don't deny that, but they also introduce a penalty, which is a greater synthetic complexity. I mean, they're not so easy. Well, I don't know, maybe they're easy for you. But you know, so I mean so I guess the question is, how do they then perform? Is there all, I mean, so take that as a given that one reason to do block copolymers would be to oppose that phase separation. But having done it, then the question we were looking at is there an intrinsic advantage sort of from an electronic point of view? Because we would expect there would be less disorder in the interface, but it doesn't seem from what we've done that actually gives us a net benefit in terms of the performance. We don't actually understand why the polymer systems are better, because there's reasons why you would not expect that. So that's what we got. I certainly, if there were a sort of straightforward way to make block copolymers, you know, you can then do an analysis, and Christoph Brabeck has done something like this, where you kind of include all parameters like, you know, something for the synthetic complexity, which is a cost, something for the extended lifetime, which is a benefit, and then something for the efficiency, and then work it out. And there certainly are conditions in which it would make sense in terms of the overall, let's say, energy return on energy investment to be using materials like that. It would depend that they would be relatively not much more complicated to make. And then you could probably tolerate some loss in efficiency, but it would have been nice. And it was something we hoped and sort of expected, that there would be an advantage to the performance, but we haven't seen it. Yeah.
Other questions? I just have a quick one, because I'm not allowed to ask you questions. I asked you already too many in these 25 years. But there's a lot of chemists here, synthetic chemists. And at the beginning of your presentation, you said, what are the material properties that would govern the performance and limit the losses? And you have shown some of those. Is there any way to translate those into chemical structures, so you could tell, hey guys, you should synthesize this type of molecules? Or how far are we from going to provide or suggest molecules for synthetic chemists?
Yeah, I mean, I think one of the most important things is trying to control this electron-proton coupling, which is causing the losses to ground. I guess it's that sort of, I suppose one, I mean, I don't know how to say convert this into atoms, right? But to some extent, I mean, the relationship between the strength of that coupling and the chemical structure can be worked out. And then one of the interesting things is going to be, can you design systems where the charge transfer state is not as strongly coupled to ground as it would be in a typical case. And that would have to do with where the electron wave function sits in the charge transfer state, and what part of the molecule is then involved in the coupling of that excited state to ground. So that's I mean, it's not maybe very helpful if you ask about the chemical structure, but if you're
there's a lot of theoreticians also here, and the theoreticians can do calculations to calculate some of those properties at least. So I think we need a cross ICMAB collaboration here.
Yeah.
Let's thank Jenny again.